This video lecture is on covalent bonding. We talked about ionic bonding yesterday quite a bit, and talking about how there's a transfer of electrons between primarily metals on the left side of the periodic table and nonmetals on the right side of the periodic table. That's really because those nonmetals are trying to gain electrons to be stable with a full valence set, and they have very negative, big electron affinities. And the metals on the left-hand side of the table, they really want to lose electrons and have relatively low ionization energies as we think about those. Well, this is the second type of bonding that we haven't discussed yet, covalent bonding. A couple things that are happening for covalent bonding. You've got at least one shared pair of electrons that are being shared between two nonmetals. There's a lot of things that work here. It's not really as just simple as sharing two pairs. There's a lot of forces that are working here. First of all, you have the repulsion forces that happen between those two nuclei. So they're not going to get extremely close to each other. There's going to be a limit to their distance that they can be at. Secondly, you've got repulsions that happen between electrons. Those like charges are going to want to repel each other as well. So what ends up happening is you also have an attraction between the nuclei of an atom and the electrons that are being shared in the electron cloud. If you look here at the bottom of the PowerPoint, you see this electron overlap here that's happening. This electron overlap really shows how the bonds are forming at the bottom here. You can see how you have a nuclei, and then this overlap is where that electron pair is at. So that's a little bit different in terms of thinking about the bonding and what happens. So they don't ever get super close together where they're right on top of each other, but they are attracted pretty strongly because of the opposite charge between nuclei and the electrons. When we think about the sharing of electrons and how those work, we have different types of covalent bonds. We have polar covalent bonds. Polar covalent bonds versus nonpolar. Polar covalent bonds means that there is an unequal sharing of valence electrons. If you look at this diagram here of HF, fluorine is the most electronegative element on the periodic table. It's almost a tug-of-war of electrons in that electron cloud. The darker red that is shows where the electrons have a higher probability of being. The blue shows that the electrons have a lower probability of where they would be here. So notice that fluorine is really pulling electrons in this direction in the structure. So this almost is not a full transfer, but it's really close. And sometimes we call this a partial negative, and this becomes a partial positive charge on this side. Thus we get two distinct ends to the molecule, a partial negative and a partial positive, thus making it polar. Notice over here that if we take and split this electron cloud between the two fluorines exactly equal, the electron pulls are exactly the same. Fluorine is the most electronegative element on the table, and it pulls with an electronegativity of 4.0. This fluorine is pulling for electrons in the bond also at 4.0. So what this results in is a tug-of-war stalemate for these electrons, and they're not pulled to one side or the other. Notice you're not getting a positive charge, a partial positive or a partial negative. We would call this molecule nonpolar. Nonpolar meaning the electrons are not spending their time pulled to one side of the molecule over the other. Whereas in the other case, electrons are going to be more likely found by fluorine based on the electrons and the pull and the electronegativity that we see. This electronegativity is a handy chart to think about. Notice that electronegativity in general as you move across the periodic table increases. So if you went from lithium all the way across to fluorine, you would find electronegativity would go up. And that makes sense because of the pull for electrons. This doesn't really have to deal with energy totally. It has to deal with filling those valence shells. It has to deal with them trying to pull electrons themselves. One guy named Linus Pauling came up with a scale to try to put this together, and it's the most accepted one. As you move down the periodic table, see that electronegativity would decrease. These elements at the bottom are a little bit bigger. Remember, their atomic radii are larger. Those electrons aren't pulled quite as strongly because of the effective nuclear charge that we've got with all those energy levels. But this trend goes a long way in helping depict polar versus nonpolar bonding. If we happen to have an element, for example, like nitrogen, and it was in a covalent bond sharing a pair of electrons between it and, say, sulfur. If you find them on the periodic table, nitrogen has an electronegativity of 3.0 for its pole, and sulfur's at 2.5. In general, if those are different numbers, we may see the electrons more closely pulled towards the nitrogen. We could expect that to be a polar bond. If you have something like the fluorine example we had earlier where they cancel each other out, or let's say we had two chlorine atoms that were bonded covalently, and this line is a shared pair of electrons. This chlorine would pull for electrons with its strength of 3.0, and this chlorine would pull for electrons with a strength of 3.0. So based on how those electrons are being pulled, they cancel each other out. This is definitely nonpolar, because the pull for electrons in the chemical bond is the same between both types of atoms. So that's definitely nonpolar. So talking about these a lot more in detail, a polar covalent bond is not as simple as just electronegativity. It's more detailed than that. If you have electrons that are being shared unequally, a bond dipole usually results. Now, this is kind of a different term, this bond dipole is. A bond dipole has this symbol mu. You maybe seen this in physics with like the force of friction or the coefficient of friction. But it really refers to here the dipole moment, or how much we can actually quantify that electrons are being pulled in a chemical bond. The equation for that is written here. You see that the dipole moment is equal to the product of the Q, or the charge, times the distance between those two different molecules. So we can actually calculate these. I'm going to show you tomorrow in class how we can calculate these dipole moments. They have a really funny unit, the Debbies, capital D, and how they're calculated. But know this, that it is a product of the size of the charge that you're seeing and their distance between them. So if you had a very small radius and there was a big amount of charge there, you could see a pretty big dipole moment, like you're seeing something with fluorine or hydrogen and how that works out. We'll work some problems out on how to do that tomorrow. The distance those bonds have, the shorter that distance is, all right, that's going to affect this overall dipole moment. All this does is help calculate the magnitude at which electrons are pulled by measuring the charges and what happens with them. Here's some examples of the dipole moments, and this chart is in your book. It's really helpful to look at. 8.3 shows you the difference between bond lengths, electronegativity differences, and the dipole moment. We'll take a look at HF in particular, and we'll look at HI secondarily. Bond length here for HF, remember fluorine is at the top of the periodic table. It has a small atomic radius. So the bond length between hydrogen and fluorine is very short, 0.92 angstroms. An angstrom is, it takes 1 times 10 to the 10th angstroms to equal 1 meter. The electronegativity difference is pretty big, and the dipole moment is large. So that really shows, see how dark red that is? That really corresponds to how much those electrons are pulled towards the fluorine. Now compare that to HI. Iodine is down in the 5th energy level, so a lot of energy shells, much bigger. The bond length is much longer because we've got bigger atoms we're dealing with. So we have a long bond length. The electronegativity difference isn't very big, it's 0.4, so the dipole moment is really limited. So a couple things to think about in these relationships, and these are kind of in-between cases. In general, if there is a short length, we got short bond length, that equals a large dipole moment. And that's the capital D. Notice how short that is and how big that is. Another thing that happens here, if we have an electronegativity difference, if it's big, that also equals a big dipole moment. Electronegativity difference, if it's big, that also equals a large dipole moment. If I can write with my mouse here. Large dipole moment. And that bears out here in these three diagrams at the bottom. You've got HF that is short with a big electronegativity difference. That's got a huge dipole moment, definitely polar. HCl has a larger bond length, but it's still a big electronegativity difference. Dipole moment still 1.08. And we'll talk about the units of that tomorrow. HBr, now we're getting a longer length. Electronegativity difference goes down. Dipole moment goes down. Then we get to these large molecules. Notice there's not any red on HBr or HI. And all that is showing is that the electrons are not distinctly pulled to one side or the other as much as HF and HCl. And it all deals with electron pull. This is kind of an introduction to how this looks. This is a Lewis structure. And we're looking at the valence electrons and how they work. So what we want to be able to do is we want to be able to predict if a covalent bond is polar or nonpolar, calculate the charges and how that looks and where those electron clouds go. Then when we do a Lewis diagram, we want to see where are those bonds at and how does that Lewis structure contribute to polarity, how does it go with geometry, and then how does that all relate to explain the behaviors of those molecules. So tomorrow we'll work homework on that section tomorrow, and then we'll talk about how this works with the dipole moments and talk about how to measure those. Thanks for watching. Make sure and take good notes, and we'll go tomorrow. Thanks.